dependent. I do Gaussian elimination of this. Become fitness. So I can subtract the first row from all the other rows. So 1, 1. Subtract that from that gives me 0, 1. Subtract that from that gives me 0, 2. Subtract that from that gives me 0, 3. Now I want to subtract 3 times this from this. Subtract 3 times this from this. So it gives me 1, 0, 1, 0, 0, 0. I see this matrix has 2 units. So that means those 2 vectors are linearly independent. Okay. So my A matrix is 1, 1, 1, 1, 1, 2, 3, 4. My A transpose is 1, 1, 1, 1, 1, 2, 3, 4. A transpose A is 1, 1, 1, 2, 1, 3, 1, 4. Times 1, 1, 1, 1. Complete the 2 by 2 matrix. Well, that row times that column is 1 times 1, 1 times 1, 1 times 1, 1 times 1, that's 4. 1, 1, 1, 1 times 1, 2, 3, 4 is going to be 1 plus 2 plus 3 plus 4. So that's going to be 3, 6, 10. 1, 2, 3, 4 times 1, 1, 1, 1 is also 10. 1, 2, 3, 4 is going to be 1 squared. 1 2 times 2 is 4, that's 5. Plus 3 times 3, that's 9 plus 5 is 14. Plus 4 times 4 is 16. Plus, what did I say? 14? Is 16 plus 14 is 30. So that's what you want to make. It's invertible. You can check. You already knew because those vectors are linearly independent that it was invertible from the lemma. But we can compute the determinant. It's going to be 4 times 30 is 120. Minus 10 times 10 is minus 100. 120 minus 100 is 20, which is larger than 2. So we can compute the inverse of this matrix. 4, 10, 10, 30, 1, 0, 0, 1. Let's see. 4 times 5 halves is 10. So multiply this row times 5 halves and subtract from this row. 5 halves times 4 is 10, so 10 minus 10 is 0. 5 halves times 10 is 25, minus 30 is 5. 5 halves times this minus this is minus 5 halves. 5 halves times 0 is 0, minus 1 is 1. Let me divide this row, the bottom row, by 5. That will get me 0, 1, minus 1 half, 1 fifth, 4, 10, 1, 0. 10 times the second row from the first row is going to give me 4, let's see, 0, 1, minus 1 half, 1 fifth. 10 times that minus that is 0. 10 times that is minus 5. Subtract from 1 is 6. Did I do that right? 10 times that is 5, negative 5. Subtract negative 5 from 1 is 6. 10 times that is 2. Subtract from 0 is minus. divide this row by 4. Make it 0, 1 minus 1 half. 4 by 1, 4 by 4 is 1, 0 by 4 is 0, 6 by 4 is 3 halves. Minus 2 by 4 is minus 1 half. So that's my inverse. My projection matrix is going to be 1, 1, 1, 1, A. There's A transpose A inverse. 1, 2, 3, 4. Times 3 halves minus 1 half minus 1 half 1 4. Times A transpose is 1, 1, 1, 1, 1, 2, 3, 4. Okay. This is going to give me 3 halves minus 1 half is 1. 3 halves minus 1 half times 2 is minus 1, so that's 1 half. 3 halves minus 3 halves is 0. 3 halves minus 4 halves is minus 1 half. Minus 1 half plus 1/4 is minus 1/4. Minus 1 half plus 2/4 is 0. Minus 1 half plus 3 halves is 1/4. Minus 1 half plus 4/4 is 1 half. So this is going to give me my projection matrix on U is going to be 1 times 1 plus 1 times negative 1/4. That's 3/4. I have 1 half plus 0 is 1 half. I have 0 plus 1/4 is 1/4. I have minus 1 half plus 1 half is 0. I have 1 minus 2/4 is 1 half. I have 1 half minus 2 times 0 is 1 half. I have 0 plus 2/4 is 1 half. I have negative 1 half plus 1 is 1 half. I'm going to have 1 minus 3/4 is 1/4. I have 1 half minus 3 times 0 is 1 half. I have 0 plus 3/4 is 3/4. I have negative 1 half plus 3 halves is 1. I have 1 minus 1 is 0. I have 1 half plus 0 is 1 half. I have 0 plus 4/4 is 1. And I have negative 1 half plus 4 halves is 3 halves. That's my projection matrix. Great. Does this make sense? I computed the projection matrix. Let's get a vector that's not in the span of these two. Let's see. I'm going to guess that 1, 1 minus 1 minus 1 is not in the span of those two vectors. That could be wrong. Let's compute the projection of that. That's going to be, let's see. I can pull out the smallest denominator is 1/4. So I have 1/4. That's 3. That's 2. That's 1. That's 0, that's 2, that's 4, and that's 3. Times 1, 1, minus 1, minus 1. That's going to be 1/4. I get 3 plus 2 plus -1, so that's 4. I get 2 plus 2 minus 2 minus 2, that's 0. I get 1 plus 2 is 3, minus 3 is 0, minus 4 is minus 4. I get 0 plus 2 minus 4, that's minus 2, minus 3 is minus 5. So that should be my projection. How will I know if it's my projection? I know it's my projection if I can subtract this from this and get something perpendicular to this. You.
Should the number in the bottom right corner of a projection matrix be a 6 instead of a 3?
It should be a 6. Because I hold out on 4. So yes. So that should be, let's see, 0 plus 2 minus 4 is minus 2, minus 6 is minus 8. So that's going to be the vector 1, 0, minus 1, minus 2. Let's subtract this from this. 1, 1, minus 1, minus 1. Minus 1, 0, minus 1, minus 2. That's going to be the vector. 1 minus 1 is 0. 1 minus 0 is 1. Minus 1 minus 1 is 0. Minus 1 plus 2 is 1. Did I do that right? I think I did. Is this vector perpendicular to this vector? Minus 1, minus 2. That's how it. 0, 1, 0, 1. That's not perpendicular. I guess I did something wrong. Is this guy in the span of these two? Let's see if I multiply that matrix times 1, 1, 1, 1. Because it's in that subspace, it should stay the same. It should be changed by the matrix. So 3, 2, 1, 0 times 1, 1, 1 is going to be 3 plus 2 plus 1 is 6. Divided by 4 should be 1, but it's not. So I have done the wrong thing. Is that matrix my inverse? Oh, good. It was a 1 over 5 there, it should be 1 over 5. Okay. So that means I should have a 1 over 5 here. So that means when I multiply that times that, I get a negative 1/2 plus a 1/5. This is going to be a pain in my neck. Negative 1/2 plus 1/5. Negative 1/2 is minus 5/10. 1/5 is 2/10, so that's going to be a minus 3/10.
I have a question.
Yes.
Why are you multiplying the rightmost matrices first versus the leftmost?
Why am I doing what?
why you, looks like you're multiplying in the equation, the
Here.
rightmost matrices.
Down three. Or
Down
down two,
here.
no, sorry.
Yeah. Looks like you.
I should be multiplying this times this. Okay. So I have A transpose A inverse. Sandwich between A and A transpose. A transpose A inverse is this thing. That's A transpose and that's A. Okay.
It doesn't matter which one you do first.
No, it doesn't matter which one I multiply first. Matrix multiplication is associated. I can do it either way. Let me erase this stuff. If you see me making that mistake, catch me soon. Minus 5/10 plus 2/10 is minus 3/10. Minus 5/10 plus 4/10 is minus 1/10. Minus 5/10 plus 6/10 is 1/10. Minus 5/10 plus 8/10 is 3/10. All right. Grand. I need to, let me pull out a 1/10. So this will be 1/10, 1, 1, 1, 2, 1, 3, 1, 4. And I should have 10, 5, 0, minus 5, minus 3, minus 1, 1, and 3. Can I do that? Yeah. You see what I did here? I took out a 1/10 because scalar multiplication means matrix multiplication. And then I multiplied everything here by 10 to get this. So this is equal to 1/10. I get 10 minus 3 is 7. I get 5 minus 1 is 4. I get 0 plus 1 is 1. I get negative 5 plus 3 is minus 2. I get 10 minus 6 is 4. I get 5 minus 2 is plus 3. 4. I get 0 plus 2 is 2. I get negative 5 plus 6 is 1. Let's see, I have 10 minus 9 is 1. I have 5 minus 2 is 3. I have 1 plus 2 is 2. I have, that should be 1 times 1, 10 is 10, minus 9 is 1. I have 5 minus 3 is 2. I have 0 plus 3 is 3. I have negative 5 plus 9 is 4. And then last but not least, I have 10 minus 12 is negative 2. I have 5 minus 4 is 1. I have 0 plus 4 is 4. And I have negative 5 plus 12 is 7. That's my projection matrix. So if I multiply that, 1/10, 7, 4, 1, minus 2, 4, 3, 2, 1, 1, 2, 3, 4, minus 2, 1, 4, 7, times 1, 1, minus 1, minus 1. I'm going to get 1/10. I have 7 plus 4 is 11, minus 1 is 10, plus 2 is 12. I have 4 plus 3 is 7, minus 2 is 5, minus 1 is 4. I have 1 plus 2 is 3, minus 3 is 0, minus 4, that's minus 4. I have, let's see, negative 2 plus 1 is negative 1, minus 4 is minus 5, minus 7 is minus 12. This guy, I can tell just from looking at it, is orthogonal to that, right? Is not what it needs to be. So this guy should be in the span of these two vectors. If I subtract this from the original vector, it should be orthogonal. Should be orthogonal to this, and it should be orthogonal to both of those. So 1, 1, minus 1, minus 1, minus 1 over 10, 12, 4, negative 4, negative 12. That's going to be 10 tenths minus 12 tenths is negative 2 tenths. I have 10 tenths minus 4 tenths is 6 tenths. I have negative 10 tenths plus 4 tenths is minus 6. I have minus 10 tenths plus 12 tenths is minus 2 tenths. So that should be, that's my projection. That should be the perpendicular to that projection. If I take the dot product, 1 over 10, minus 2, 6, minus 6, minus 2, with 1, 1, 1, 1, you see that I get 0. If I take the dot product of this guy, with this guy, so that's 1, 2, 3, 4. 1 over 10. So that's negative 2 plus 12. Let's see, that's minus 18. Is this going to give you the right thing? Minus 8. Oh, this should be plus 2. Plus 8. You see that I get 0. So this vector is perpendicular to that whole plane in 4 dimensions. Question?
I'm trying to figure out, because I think you need a positive 2 on the bottom for the 1/10 on the vector.
Here?
Yeah.
Okay, so I have negative 10 tenths.
Yeah.
Negative, negative, that's positive 12 tenths. This gives me a positive 2. And I use that positive 2. So this guy is perpendicular. So let's check this out. If I add this guy to my projection, I should get back to where I started. So 1 over 10, 12, 4 minus 4 minus 12, plus 1 over 10, negative 2, 6, negative 6, 2. I'm going to get 12 tenths minus 2 tenths is 10 tenths, that's 1. And here I'm going to get 4 tenths plus 6 tenths, that's 1. Down here I'm going to get negative 4 tenths minus 6 tenths, that's minus 1. And here I'm going to get negative 12 tenths plus 2 tenths, that's negative 1. Get back to our study. Does that make sense? So that's how you compute these projections. Let's compute this. What happens if I multiply this projection matrix times this vector which is already in my plane? So 110 7, 4, 1 minus 2. 4, 3, 2, 1. 1, 2, 3, 4. And negative 2, 1, 4, and 7. Now multiply that times 1, 1, 1. The closest vector in this for this vector that's in that plane is this vector. It's just 0 to itself. So this should be equal to itself, is it? I'm going to get 110. 7 plus 4 is 11, plus 1 more is 12, minus 2 is 10. 4 plus 3 is 7, plus 2 is 9, plus 1 more is 10. The same thing here, 1 plus 2 is 3, plus 3 more is 6, plus 4 more is 10. Negative 2 plus 1 is negative 1, plus 4 is 3, plus 7 is 10. What about 1, 2, 3, 4? That's going to be 1 over 10. I have 7 plus 4 times 2 is 8 is 15. Plus 3 more is 18. Minus 2 times 4 is 28. So 18 minus 8 is 10. 4 plus 3 times 2 is 6, that's 10. Plus 6 more is 16. Come on there. 4 plus 6 is 10. Plus 6 is 16. Minus 4 is 10. simple source 20 variables. I can do it with dimension 1, plus 4 is 5, plus 9 is 9 plus 5 is 14. Plus 16 is 30. Negative 2, plus 2 is 0, plus 14 is 12. 12 plus 4 times 4 is 28. 12 plus 28 is 40. So indeed it's the case if I multiply that projection matrix times either these two vectors, I just get the vectors. So here's what that means. Projection matrix on U times some vector B. Well, that's in the subspace. Once it's in the subspace, if I try to project it on U again, it's already in U, so I just get it back again. So it's that's important. Remember. So here's a theorem we just proved. If I take the matrix, a projection matrix, and multiply it by itself, it's the same thing as projection. That's going to be kind of important too. Why are projection matrices important? So let's consider this. You guys are engineering students, right? Have you ever flown on a plane that got into during turbulence? What's going on is this. How many variables describe motions of an airplane? Many, 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 right? How many of those variables do you think you can control? Few. What you're going to do is you're going to project the very many variables in the motion of an airplane onto a few variables that you know how to control, and you're going to work with those. Because that means that instead of working with very many differential equations, you just have to work with a few. Okay. Did I take pictures of this? I did.
That was the first to take one, I guess.
None of this.
Right.
Yeah, I don't really say. Okay. Let's draw a picture. Picture's graph. going to draw some measurements that I hypothetically made of a control and response. If you squint your eyes, what do you see there? This is a new trend. So we can feel brave, and we can just go a straight line through that scatter gauge. Or we could try this. I'm thinking I made some mistakes when I measured those data points. Did I make mistakes? Why not? So I have a whole bunch of x's. 1 and 2 and 3. Xn. And I measured measurements y1, y2, y3, y9. But what I really should have had is yi. Ideally, I should have measured a yi hat. Yi hat was going to be m, some slope, times xi, plus some intercept. So I could try to pick those data points it would look like that, which doesn't reflect anything other than maybe I had a slightly shaky hand. Really critical thing for me to understand is what the slope of the intercept is. Okay. So the notion is that, okay, I don't know what M and B are, my slope and my intercept are. So whatever they are, I should look at yi minus yi hat. The true value I should have measured but couldn't, because I'm sloppy. And this depends on M and B. And this is what's called my error. So I want to find the M and the B that minimize my error. So let's see. If I think about this a little bit. My vector is vector on 1 to yn. This belongs to Rn because I measured real numbers. Okay. I think my true value y hat 1 through y hat n should belong to belong to what? It should belong to the two-dimensional subspace that I get from my N and my D. So that's going to be x1, x2, down to xn, 1, 1. 1's all the way down, times the vector n. So my true value is going to be in here. And it should be the point in here that makes this distance small. I have to take the distance squared. Make that small instead. Now, if you think about it for a minute, you'll realize that the distance will be smallest, and the distance squared is smallest. So I'm trying to find out the vector in the plane spanned by this vector and this vector. That's as close as possible to this. Which vector will that be? The vector in the plane spanned by these two vectors. It's as close as possible to that. Anybody tell me? If I take this guy and make it as small as possible, well, let's see. I have a two-dimensional subspace. I have some vector. Which vector in this plane is as close as possible? We've been talking about it. How do we get the vector in a plane that's as close as possible? It's not in the plane. It's going to be the projection. Okay. So y hat is the projection theorem. Y hat is the projection of y on the plane. What should we call this matrix? Call that matrix A. A times M. Luckily, we know how to compute projections. So let's see. The projection on the plane is going to be A times A transpose A inverse times A transpose times y1. That's equal to 1 half. Now, Really though, we don't want the projection necessarily. What we want is the m and the b. But the projection is y hat is going to be a times the m and the b. That means the slope and the intercept is going to be a transpose a inverse times a transpose times y1 y. So let's see, what is a transpose a? Is going to be x1, x2, xn, 1, times x1, xn, and then 1. So this 2 by 2 matrix, what I get is going to be x1 times x1 is x1 squared, x2 squared, all the way down to xn squared. So this is xi squared. This times this is going to be the sum of the xi's. This times this is going to be the sum of the xi's. And this times this is going to be n. Pictures. So it transpose A inverse. It's going to be the inverse of that matrix. How does that go? What is the determinant of that matrix? Determinant of A transpose A is going to be n times sum xi squared minus sum of the xi's squared. So the inverse should be 1 over n times the sum of the xi's squared minus xi squared. What's the formula for finding the inverse? Dividing by the determinant, switching these two guys and making those two guys negative. N negative sum of the xi and what do I think about that number? It has a name. Let me try and write it a little differently. Let me make this as n squared times xi squared over n minus 1 that number? You should have had in the lab. Should have written it in the lab report. I have pin numbers. I add them up and I divide by the total number. No? Feel it.
Yeah.
No. Feel it.
The average?
The average. So call this number X bar. Call this number X squared bar. So I have n squared, X squared bar, minus X bar squared. That has a name too. You know what the name is? Here's a hint. If the xi's were constant, xi squared would all be the same number. Okay? And those two things would be equal to each other, so you get 0. This has a name, it's called the variance. Have you ever heard the variance? Who's heard for the variance? One, handful of people. It measures the dispersion of the point. It's called sigma squared, is usually the symbol we use. So this is going to be let's see, 1 over n squared, sigma squared, times n this is the determinant already. So that's my determinant there. I need to multiply that by n. So that thing is equal to this thing. So I have n squared sigma squared. Good. I have n. I have minus xi's. I have minus xi's. And then xi squared. So now let's compute my slope and intercept. I need to multiply this, m, v, is going to be 1 over n squared, sigma squared, n, minus the sum of the xi's, minus the sum of the xi's, sum of the xi squared, times x1, x2, it's n, 1, 1, 1, times y1, that's 1 over n squared, sigma squared. If I multiply this times this, n minus xi, minus xi squared, I'm going to get a 2 by 1 matrix, which is the sum xi, yi, and I'll get the sum of the yi. So this is going to be 1 over n squared sigma squared. of the xi's times the sum of the yi's. And then I will have minus sum of the xi's times the sum of the xi's plus sum of the xi squared and the sum of the yi's. That's my slope minus. When you do a linear regression on your calculator, this is what it computes. Does that make sense? Can I simplify this a little bit? Let's see. This is going to be 1 over sigma squared. I'm going to have 1 over n, sum xi yi. And then I'll have minus 1 over n, the sum of the xi. 1 over n, the sum of the yi's. And then I'll have minus 1 over n, the sum of the xi's. 1 over n, the sum of the xi yi's. Plus 1 over n, sum of the xi squared, and 1 over n, sum of the yi's. So we can write this as 1 over sigma squared. X times y bar, the average of x times y, minus 1 over n xi, that's x bar, 1 over n y, that's y bar. That's the average of the x, that's the average of the y. That's the average of the x times the y. And then I have minus the average of the x's times the average of the xy's plus the average of the x squared times the average of the y's. So these are all basic statistics you can compute. Does that make sense? That is called linear least squares regression. Least squares, because we're trying to minimize the squares. It is one of the most important statistical tools you have for trying to deal with data. And if you aren't dealing with data, you're doing mathematics, pure math. All right. The thing is, we don't have to stop there with the linear regression. What should I do if my data is this? That's kind of a trend, it's not linear change, is it? So we might say, okay, I have my x1, y1, xn, yn. I have a bunch of data. But if I try and draw a straight line through that, it's not going to be a good fit. So, okay, I put on my thinking cap and I say, look, my y hat I, my ideal y, should be maybe some quadratic function of the x. Okay? Okay, let's see. That means that my y, my ideal y, should be a matrix, x1 squared, x2 squared, down to xn squared, x1, x2, down to xn, 1, 1, 1. One's in the third column, the rightmost column just like before. My ideal observations, the observations I would need if I didn't have shaky hand, should be in the three-dimensional subspace spanned by those three vectors. We call that quadratic regression. Call this matrix A, like we did before. And then the coefficients of my least squares fit of the quadratic, the A, the B, and the C, should be given by A, B, C is equal to A transpose A inverse times A transpose Y1. My measure values of Y. Does that make sense? So what do I have to do? I have to multiply this times its transpose. I'm going to get a matrix. It won't be as simple as this one, or as simple as that. I compute its inverse, multiply it by A transpose, but I can compute those because of my calculator. You know, if I multiply A times A transpose, that's a n by 3. A transpose should be a 3 by n. When I multiply it out, I should get a 3 by 3. Your calculator can compute the inverse of a 3 by 3 matrix. Not hard to do. Then I just have to multiply that inverse times the transpose of this, multiply by my column, and I get my coefficients. My quadratic A, term A, my linear term B, and my constant term C. Any questions? Why would an engineer be interested in doing this? The real world is linear, right? We shouldn't need quadratic. Real world is not. That's why you want it. If your data starts bending before you're ready to have it bend, if you can't control your system to stay within an approximately linear region of the data, you're going to need to do something like that. Does that make sense? That's all.